So picking up where we left off, talking about polynomials, well, we have these polynomial functions. One of the things that we want to do with them then is start to graph them. So there are some important things that we need to know, just a few helpful things about polynomials that we can use when we start graphing these functions. The first thing that's helpful are our intercepts. And specifically, we don't really talk about the y-intercepts too much at this point anymore. I'm really focusing on the x-intercepts, which may also be called roots. You may also hear them called zeros. It all means the same thing. X-intercepts, roots, zeros, solutions, it all means the same thing. But what I'm especially concerned with here, A is where are they, obviously, but also what happens there. And I'm not going to talk about this much right now because we're going to talk about it later on in the chapter. But one thing that is helpful when we start graphing these polynomial functions is where are all of our zeros? Well, in this case, we can kind of see it. They're right here. 1, 2, 3. I'm just going to call them A, B, and C for now. Right, so we'll deal with that later. Another thing we'll deal with later, well, we're not really going to deal with much at all in this section, is the concept of domain. And you may have heard this word before. It's not all that interesting with a polynomial function, but just to keep in mind, what I'm talking about with domain means just what x values am I able to actually plug into the function? Or more specifically, what x values can I not plug into the function? So another way to say that is what x values are excluded. And for now, we're not going to deal with this. It's not all that interesting for a polynomial function because a polynomial function, there are no restrictions on what I can plug into the function. I can plug in any number I want, right? There are no restrictions. I can plug in whatever number I want and I will get a number in return. So we're not going to worry too much about the domain. The last thing, and the thing we're going to focus on here, is something called end behavior, and that's new. And the answer is kind of in the name. We're talking about the end behavior. Well, we're talking about what happens at the ends of the functions, right? So my end behavior, I'm going to concern myself with what happens in these parts that I just highlighted in green, right? How can I tell where the function is going? So that's how I'm going to write it, right? Where does the graph continue? As x does one of two things. As x gets bigger, or what I'll say, normally we would say or smaller, but in the interest of being precise, our number is not necessarily getting smaller as much as it's getting more negative. Right? I could have a really large negative number, right? Negative 1 million is not a small number. That's a large negative number, right? If I'm $1 million in debt, that is not a small debt, right? So as x gets bigger and bigger and bigger, or as it gets bigger but it gets negative, right? So like negative 1 million, my example from before. And so for this section, we're going to focus right here. We're going to focus on end behavior. So the question is now, how do we deal with end behavior, right? How do I figure out what the end behavior of my function is? Well, there's a really easy way to do that, and we need to consider two things. I'm going to look at my degree, right? Remember we said that this was the highest power of a function. And the other thing I'm going to talk about is the sign of the leading coefficient. Right, so that leading coefficient plays a pivotal role in telling us about how to graph our function. Well, my degree can be one of two things, right? It can either be even or odd. And the leading coefficient can be one of two signs, right? It can be positive or it can be negative, and that's as simple as just looking at the number. If it's a 3, it's a positive 3, and if it's a negative 3, it's obviously a negative 3. So if I put these together, right, if I have an even degree and a leading coefficient, well, let's kind of talk about this analytically right now. If I were to talk about maybe an even degree, I'm just going to abbreviate here, and a positive leading coefficient, I want to think of an example function that would be helpful for me to understand how this works. And the simplest thing I can think of is just x squared. Leading coefficient is positive 1, and the degree is 2, which is an even number. Well, if I were to graph just kind of a mini version of this, just for the sake of space, right, well, my graph is going to look like it's a parabola, right? We talked about this in the last chapter. And well, what happens at the ends of the functions? We can see at the ends of the functions, so at the ends of the functions, right here, we see that the graph increases on both sides. And it turns out that for every even degree function with the positive leading coefficient, that is true. So one of the great things about coming up with these small tricks, these small examples, is it's really helpful when we think about bigger, more complicated examples. So anytime I see something with an even degree, and a positive leading coefficient, I know that it's going to behave like my x squared example over there. And we learned that my x squared example, right, something happens on the ends and it increases both sides and the ends. We don't know with the functions what happens in the middle. We don't care right now what happens in the middle. All we care about is what happens on the ends. And I know at the ends, it increases on both sides. So it increases on the left and the right. Let's look at kind of the negative case of that. So if I look at a function with an even degree and a negative leading coefficient, well, I can still stick with my x squared example, but now I'll call it negative x squared. And one of the things we learned about, not where I want to do that, one of the things we learned about is whenever I see this negative, it takes my graph and it flips it over the x-axis, right? It reflects it over the x-axis. So my graph kind of looks like this. And what happens on the ends? Well, instead of increasing, now I'm decreasing. Right, so I can kind of take this and transfer it over just like I did before. I don't know what happens in the middle with my specific functions, but I know on the end it's going to decrease on both sides. Decreases toward the left and decreases toward the right. So we're going to say that it behaves a lot like negative x squared. So they're my even functions. Just for some room, I'm going to get rid of my small examples over here. So we can talk about what happens when these functions are odd. So when these functions are odd, we're going to follow the same logic. I need a function with an odd degree and a positive leading coefficient. Well, you might think of y equals x, but I want something that's a little more interesting. So maybe not the most basic example I can think of, but something that's still rather basic and rather simple is x cubed. And that's going to look like, to draw my axes here, that's going to look like this. Right, it's going to kind of taper off and then increase again. So I've got this kind of S-curve figure. Well, what happens on the ends? Right, I can see on the ends that to the right I'm increasing, but to the left it's decreasing. So we're going to say that this is going to behave like x cubed. No matter what happens with the function otherwise, if it's an odd degree and a positive leading coefficient, my graph is going to look like x cubed. Well, what does that look like? To the left it's going to decrease, and we don't know what happens in the middle, but we know that to the right it's going to increase. So we'll say it decreases to the left, and it increases to the right. So if we think back to what happened with going from x squared to negative x squared. Logically, right, if we use our intuition, I can consider what happens if I have, if I have an odd degree, but a negative leading coefficient, right? If I consider something like negative x cubed, well, using our intuition, it would stand to reason that the same idea is going to happen as before, where this negative that we've now introduced is just going to make our graph reflect over the x-axis. So now here are my ends, and we can see that reflection, right? We can see that instead of decreasing to the left, I'm now increasing to the left, and then I'm decreasing to the right instead of increasing to the right. Right, as I'm moving to the left, right, I'm starting here and I'm moving to the left, I see my function increasing. As I start here and move to the right, I see my function decreasing. So we'll say it increases, I'm just going to abbreviate so I have some room, increases now to the left, and decreases now to the right. And we're going to say, just for some completeness, this is going to behave, no matter what happens, it's going to behave like negative x cubed. This is a lot, right? This is a lot of information. There's a lot of stuff going on. Definitely go back and rewatch this part of the video a few times. It's going to help. If those little mini examples are helpful to you, then use them. If you would rather just sit down and memorize this chart, by all means do it. Whatever floats your boat. I've never been a fan of memorization in math. You guys know that. So I like to come up with examples that help me remember the material rather than just sitting down and committing it to memory, because I'm going to forget it faster that way. So based on this chart, right, based on the chart I just showed you, there are two different types of problems that we can really talk about. I could go one way and I could ask you outright what the end behavior is of a function. So in a problem like this, if I ask you directly for the end behavior of a function, you know to look for two things, right? If we go back to my chart here, I need to know two things. I need to know the degree, and I need to know the sign of the leading coefficient. So I need to know the degree, and I need to know the sign of the leading coefficient. Leading coefficient. Okay, so if I look at this, I'll use highlighter. Start with degree. Is this in standard form? Yes, it is. So my degree is just the highest power I see. That's 4. And we know that's an even degree. And then I want to know what my leading coefficient is. And there's nothing written here, right? So we assume it's a 1. We assume it's a positive 1 because there's no negative written. So I have an even and I have a positive. If I go back to my table, even and positive brings me into this box right here. From my mini example that told me that my graph, no matter what happens in the middle, on the ends, it's going to look a lot like just x squared, my upward facing, my upward opening parabola. That's what I'm going to say. So I'm going to say this right here tells me it's going to behave a lot like x squared. And that tells me it's going to increase toward both the left and the right. It's the same on both sides. It increases toward the left and toward the right. So I could ask you a problem like this, right? Here's the function, tell me the end behavior. I could also do the opposite. I could say, here's the graph. What do you think the degree and the leading coefficient are? So here's the graph. Let's figure some stuff out. So we're going to break it down this way. We're going to say, what happens as I move to the right? And what happens as I move to the left? All right, well, if I'm moving to the right, and I look at the end on the right here, as x increases to the right, my function's also going to increase. You can see it moving upward. So to the right, it's increasing. To the left, I do the same thing. I look at my end over here. I can see it decreasing on the left. If I go back to my chart, I want increasing to the right, decreasing to the left. So increasing to the right, decreasing to the left. Here it is. Increasing to the right, decreasing to the left. Puts me in this box, which is for an odd degree and a positive leading coefficient. So I know that the degree is going to be odd, and the leading coefficient is going to be positive. Let me put that in a different color so it sticks out. There we go. All right, so increasing, I'm going from low to high across my whole function, right? I went from low to high. That tells us from our chart, it's an odd degree with a positive leading coefficient. So two different types of problems I could ask you if I'm asking specifically for end behavior. One of the things we're going to start doing in a bigger context, though, is starting to graph these functions. So I'll walk through one, and then you can have, there'll be a second one I'm going to walk through, but you can pause the video to try it on your own if you want. We're going to talk throughout this chapter about how to graph and different strategies we can use to graph as accurately as possible. But for now, we're just going to plot points. We're going to plot smart points, but we're just going to plot points. So here's my function. I have negative x cubed plus x squared plus 3x minus 3. So I want to start by figuring out, well, we talked about end behavior, and it would be helpful to know that. It's going to give me a sense of direction. So what do we know about the end behavior? Well, we know that the degree is 3, and that's an odd degree, and that my leading coefficient, such a long phrase, is -1, right? It's a negative leading coefficient, right? So here's my degree. Here's my leading coefficient of -1. We assume that 1 is there. So I have an odd degree and a negative leading coefficient, and if I go back to my table, odd degree, negative leading coefficient puts me in this box down here. Tells me I'm going to increase as I move to the left and decrease as I move to the right. I'm moving from high to low. So we're going to write that down. It might not be useful right away, but it will be useful later, even if I just draw the sketch of what the picture looks like. The next thing that's going to be helpful are some points, right? I said for now, it would be helpful just to have some points because we haven't talked about how else we can graph. So I'll come up with a little table here. If I do, usually pretty safe to pick -2, -1, 0, 1, and 2. If I plug those into my function, I did it on a calculator ahead of time to save myself some time, but if I plug in -2, I get 3. -1 gives me -4. 0 gives me -3. 1, 0, 2, -1. So now I have a whole bunch of points I can plot. So if I do -2, 3, -1, -4, 0, -3, 1, 0, and 2, -1. All right, well, this is great, but the question is, what do we do with it now? Well, our end behavior is going to tell us, right, as I move to the left, I need to increase. As I move to the right, I need to decrease. So I'm going to plot my points kind of as best I can with that end behavior in mind. So I'm starting up high, and I need to get through my first point, and I missed completely. So I need to get through my first point. And I get over here and I need to get to my third point at 0, -3, so I'm probably going to turn around here somewhere. I'm going to move up, and then I need to catch this one too. I should turn a few times in the middle of this graph. Because it's cubic, it's that third degree. I know I'm going to have some turns throughout the whole thing. This would kind of be my way of doing that. So there's my graph. It's just a sketch. So one of the key things is this word right here, sketch. It doesn't need to be perfect yet. We'll talk about ways to make it better later. But for now, it's just a sketch. So 2 steps, right? Talk about my end behavior. 2 steps. Talk about my end behavior. Plot some points. And then eyeball it as best as you can. It's not going to be perfect yet. And it feels a little bit old school because we have our calculators that can do this for us. Part of why we sketch graphs still is to understand how these things work, right? If you're making the graph yourself, you're understanding how the graph is functioning, all these characteristics, what they mean. So that way, if you were to see a graph like this in like a news report or in the media, you understand what's going on. So our second example here, sketch the graph of x to the fourth minus x cubed minus 4x squared plus 4. Same deal. If you want to pause the video to work on it on your own, you are more than welcome to, but I'm going to go right ahead and jump in. So just like before, I want to talk about the end behavior of my graph first. And I notice that I have a degree of 4 this time, which is even. And my leading coefficient, I'm just going to abbreviate this time, is 1, right? Nothing written there. We assume it's a 1. That's odd. Sorry, we're not looking at odd there. We're looking at positive there. So even degree, positive leading coefficient. I might as well just spell it out all the way. If I go back to my table, even degree, positive leading coefficient behaves like x squared, where I'm increasing on both sides. No matter what happens in the middle, I'm rising on both ends. So maybe I'll sketch that just to have my picture there, just to have a visual. And now I'm going to plot some points. Always helps to have these points, just like a little, right, checkpoints, no pun intended. Just some checkpoints along the way to make sure I'm kind of guiding my work. I have a guideline, I guess would be another way to talk about these points. 0, 1, and 2. Usually safe picks. Same thing, I did this on a calculator already to save myself some time. So you're not staring at this video for 25 minutes just watching me try to do arithmetic. So if I plug in -2, I get 12. If I plug in -1, I get 2, 4, 0, and -4. So I'm just going to count by 2s actually up my scale, up my graph, just so I have the room to actually plot all of this. So I'll count by 2s on the y-axis and 1s on the x-axis, which is going to make some mathematicians that are seeing this scream a little on the inside, but for our sake, it's okay. So I'm going to plot this at -2, 12, so 2, 4, 6, 8, 10, 12, -1, 2, 0, 4, 1, 0, and 2, -4. You got to pay attention to the end behavior here, because based on just the points alone, you might think that the graph is going to kind of go this way. But that's not what our end behavior is telling us. Right? Our end behavior is telling us I need to increase on both sides. So no matter what happens, let me keep the colors the same. Toward the left, I got to increase, and toward the right, I have to increase. So if I go to sketch my graph, I'm going to start by moving this way, and logically I need to turn a little bit and turn a little again, and then I come to this point down here. Our end behavior is what tells us, is how I know that I need to turn around again and increase. Right? I cannot just keep going negative, keep going down, because my end behavior over here over here tells me that I need to increase as x gets bigger, which is how I get my graph on the end. Again, this can be a little bit different. It can be a little confusing because the material is pretty new, but with a little bit of practice and maybe a little bit of rewatching, you'll be able to get the hang of it too.